Thanks, Sid, for inviting me. I'm glad to be here. And today I'll talk about finding correlations with very few samples. And this ties in very well with what Sriram spoke about. In his talk, he mentioned that often in biological data, even though it looks like we have a lot of data, it's still not enough because the number of features is humongous. It's in the millions. And that's the sort of problem that I'm going to talk about today. So just as a quick preview of what's to come, there are three parts in the talk. The first part is what are graphical models. I'll just talk about the basics, what the definitions are at a very high level. And then I'll talk about two recent works on learning a particular two popular classes of graphical models, the Gaussian graphical models, which are very popular for modeling continuous data, and the other one, Markov random fields, for modeling discrete data. And there's a lot of theory, statistical theory, as well as computational analysis that goes into these, the stuff I'm going to speak about today, but I'll ignore all of that. I'll only focus on the algorithms, right? So the statisticians, if they see it, they might not, they might come after me, but I'm only going to talk about algorithms. So what's underlying our inference methods? Okay, and these will be two new algorithms that I'll talk about. New in the sense that those were not known until very recently, just a couple of years ago. So to get us started, so what are graphical models? And so these are models for generating data. As Sriram mentioned, these are ways that we think of generating artificial data. But these are models which hardcode certain kinds of dependencies, right? And they're great for modeling statistical relations between various features that you both see when you directly look at the data and those you don't even realize are there. And one of the cool things about this is that it exploits and connects two different areas. One is probability theory, statistical theory, and so on. And the other tools from graph theory, as we will see. And today I'll only focus on one half of this whole theory, graphical models, which is undirected graphical models. So the graphs for us will be undirected graphs, and there's a whole parallel world of directed graphs or Bayesian nets and so on. And this area actually has its origins independently in many different fields. It shows up in social sciences long ago. It shows up in statistical physics. It shows up in statistics, as you can see, and in machine learning, vision, and so on. As a result, there are also many names for it, probabilistical graphical models, Markov networks, Markov random fields, and so on. Today, I'll just use the term Markov random fields for the most part, and sometimes graphical models. Okay. So what are graphical models? So suppose you have some distribution, right, that you're getting samples from, and you are trying to construct some model for this distribution where there are nodes which you think of as corresponding to features or individual variables in your distribution. And the edges in the graph are meant to capture relations between the distributions. And often when you apply this, there are thousands or even millions of variables, as happens in human genome sequencing and so on. And here, for example, this is a protein-protein interaction network that was built by learning some kind of graphical model based on some protein interactions. Okay? So let me give a very toy example. This is clearly a made-up data set, but I want to illustrate what it means. Where does this concept come from, and why is it? At first look, it might look like an obvious thing or a silly thing, but it's subtle. And just as an illustration, here's a very toy example. Suppose you have a data set where you collected some data set from individuals. Each row here, think of it as a person, their age, their marital status, and high blood pressure. Now, I just made up these numbers, but presumably if you actually go into the real world and look at data set, maybe it looks something like this, right? And do you see anything in this data set? Well, if you look at the data set more closely, you might think that being married is correlated with having high blood pressure. Okay? But is it really though? And the answer to this is that presumably around the time that people get married, maybe in their mid-30s or so, that's around the time they start developing some of these symptoms, right? So there's an underlying factor, age, which you can think of as a confounder that also showed up in Sriram's talk. So how do you model this statistically? We see it in the data set. I know this is a toy data set, but this does show up in actual real-world data sets as well. So how do you capture this? How do you model this statistically in a rigorous way? And for this, we have to use the language of conditional independence, and that forms the core of graphical models. So there's a formal definition of conditional independence here, which you can look up in any probability textbook that I won't read out. But as I said, we need language from two different areas. One is probability, especially the language of conditional independence and so on. We also need some basic language from graph theory. So graphs are what you have. A graph is basically given by a set of vertices and edges, relations between these vertices. You should think of each vertex in my graph corresponding to a feature. Right? Like there's a vertex for age, there's a vertex for whether or not the person is married, there's a vertex for whether or not the person has high blood pressure, and you're trying to infer relations between them. And two things that I'll use often in this talk are degree of a vertex, which is the number of connections each vertex has, like how many other things is it connected to. And clique, it basically means that it's a subset of vertices where they're all connected to each other. You might have a clique on Facebook and things like that. Okay. So with that, so what's a graphical model? Here's the formal definition. I have a distribution x. It's a random distribution, random variable. There are n features, x1 through xn. We'll think of each one as an individual variable. And this distribution comes with a graph associated with it, which we'll call the dependency graph of the distribution. And in the dependency graph has this feature that we really want, meaning the property that we want is that whenever there is no edge between two vertices, let's say I and j here, there's no edge, then we want them to be independent once I condition on the remaining vertices. Okay? So the graph is kind of counterintuitive because it gives more information when there is no edge between vertices, right? So when there's an edge, it doesn't mean as much. But when there's no edge, it tells a lot that you want them to be independent, but not directly, but once you condition out the neighbors. So for example, if you go back to my toy data set, here's what the graph should look like. I have a node for being married, I have a node for having high blood pressure, I have a node for age. And if you just looked at the data set, marriage seemed to be correlated with high blood pressure, but there's an intermediate node, age. Once I conditioned that, they became independent. That's exactly encoded in this graph. And you can have a lot more complicated graphs. It doesn't have to be a simple like graph. You can have cycles, you can have large cycles and so on. And here I have a cycle. There are 4 variables A, B, C, D. And if I tell you that this is a dependency graph of a distribution, this means that the variables A and C are independent or become independent of each other once I condition on B and D. Okay? So that's the definition of graphical model. And they are everywhere in, especially in biology. So protein-protein networks, they show up. Here's a depiction of a graphical model representation of some graphs, of some data sets. There's gene regulatory networks. They are used in fMRI data. You also try and construct a graphical model which underlies the distribution. Okay. So there are many applications. We saw some in Sriram's talk already in bioinformatics. The admixture model is a kind of a graphical model that you're trying to learn. They also show up a lot in statistical physics. This was and optimization. This was briefly alluded to in the first talk of the day, where there was this potential function and it was exponential of something, and that's exactly a graphical model as well. They also show up in vision in applications where you're trying to do scene segmentation based on trying to detect correlations. They're used a lot in natural language processing in trying to infer sentence speech structure and things like that. And of course, also broadly in machine learning in the form of Boltzmann machines and things like that. Okay. And as a result, there are also many tools and packages that you can use off the shelf for trying to infer the dependency graph or learning parameters of graphical models. Right? So what are the problems, computational problems that we'd like to solve? Right? Someone gave me a data set, and the question of learning graphical models means two things. There are two kinds of learning problems that we'd like to solve. One is called structured learning, meaning, okay, I gave you my distribution. Can you learn the dependency graph of the distribution? And so which variables are connected to each other in this much more meaningful way as formalized by graphical models. The other related question is parameter learning. So you want to learn more exact parameters. How is this distribution being generated? The example that Sriram talked about, the admixture model, was in the second class, parameter learning. There we kind of assumed that the graphical model was known, there was an underlying structure that was made explicit, and we just wanted to learn the parameters. And but there's also a sister question of trying to learn the graph itself. And today, I'll mainly focus on the first problem, structured learning, because in some sense, if you have a structured learning algorithm, once you have that, you can then do parameter learning. So what's the structured learning problem that I'll talk about for the rest of this talk? I'm given access to samples from distribution X. I go to this box and ask for something. It gives me a sample from this distribution. Let's say maybe the record, genome of some person. So initially, I don't know anything about the features, how they're connected to each other, and so on. But once I run my algorithm, I want a good guess as to what the relations between the variables are, as encoded in this graphical model, in this conditional independent structure that we mentioned. And our goal is to do this with as few samples as possible. We have very little, and often in this, where these models are applied, the number of samples is much less than the underlying dimension of the data. So you should think of n as being in the millions, and then the number of samples as much, much smaller. Definitely less than n. Okay, and as I just said, the setting in practice that you face in the real world is that the number of samples is much less than the dimension of the data. And if you just approach it in this broad generality, the problem becomes infeasible, statistically impossible to solve. Right? You just don't have enough data. So you have to introduce some additional assumption. And a very natural assumption that the statisticians made long ago is the following. So when is a dependency graph actually meaningful? Right? So if I just connect every vertex to every other vertex, I say, okay, everyone is connected to everything else, everything is related to everything else, it doesn't make much sense, and it's not very useful for me at all. Right? So this model would be most useful when I tell you that, okay, I'm only related to 5 other variables or 4 other variables, few other variables. And that's exactly the assumption the statisticians made, and that's what we will make too. So we will assume that the underlying dependency graph that we don't know, right? We are only seeing samples, we don't know what the graph looks like, and we are trying to infer what the graph is sparse. Sparse is a word that you see a lot in machine learning, and here it has a very precise meaning that each vertex we're going to assume has only few other edges, that it is few other vertices it is connected to, right? It's both statistically meaningful and also makes the problem computationally tractable. So here's a summary of the problem that I'm trying to solve. So far I've only talked about formalizing the question. So we have input, which are samples from a distribution, and our goal is to learn the dependency graph of the distribution. And the 2 main parameters to keep in mind are n, which is the number of variables, we should think of as being thousands or millions, and the d, which is the max degree of the dependency graph, which you should think of as a constant. Typically, in all these gene regulator networks, fMRI data, and so on, it's except for a few isolated vertices, it's mostly in the tens. And the ideal goal for us would be to find practical algorithms that you can implement fast, that can scale to such a high dimensional data, and have some provable guarantees that we know will work. There's a reason for trying to use them as opposed to others. Okay. And I'm actually not, I don't do much applied work. I work in theoretical machine learning and more broadly theoretical computer science, where trying to prove guarantees is sort of the hallmark. And one of the reasons we do this, or I do this, is that when you try to develop things rigorously, you might gain new insights, new algorithms that you can then go and deploy in practice. And actually might see something more as well there. All right. So that's the first part of the talk. I talked about what graphical models are. And in the second part, let me talk about a very special class of graphical models, special in the sense that they're not restrictive, but special in the sense that they're one of the most often used graphical models, Gaussian graphical models. Okay. So what are Gaussian graphical models? These are used a lot in biology and so on. So they come from a multivariate Gaussian distribution. Right? If you go up to a statistician and ask, okay, what's the distribution of this random variable? If you don't give them anything else, they'll say, okay, it's Gaussian. Right? So multivariate Gaussian distributions are one of the most versatile models we have for fitting continuous data. Okay? And here S, I denoted, is the covariance of the distribution. And what is the dependency graph of the distribution? So I have samples from Gaussian. What are the statistical relations that underlie the different features? Are there meaningful statistical relations? And this was asked back in the 50s and 60s and was answered in this really amazingly clean result by Dempster, I think, who was a statistical physicist in 1972, who showed the following. Let's look at what statisticians call the precision matrix of a distribution, defined as the inverse of the covariance matrix. So often you hear talk about covariance matrices, but statisticians have been talking about precision matrices for a long time, and for good reason. Precision matrix often encodes information that covariance matrix doesn't. And for Gaussians, it's even more stark. What he said was that dependency graph of the Gaussian distribution is exactly captured by the zeros of the precision matrix. So you have this big matrix, there will be some zeros and some non-zeros. Whenever there is a zero, those variables are conditionally independent. Okay, so the dependency graph is exactly given by the precision matrix. And now we go back to our application in mind. So you have this very high dimensional continuous data. The first guess might be to try and fit a high dimensional Gaussian distribution to this data. Can I learn the mean, the covariance of this distribution, right? But the number of samples we have is much less than the dimension. And if you use off-the-shelf learning algorithms for Gaussian, you need at least linear in the dimension many samples. So this is not possible. And here's where we'll exploit our insight from graphical models, which is that we'll assume the precision matrix, which encodes the dependency structure, is sparse, has few non-zero entries, each vertex is only related to a few others. And this leads to the problem of learning Gaussian graphical models. I'm given as input some samples from a Gaussian distribution, and our goal is to learn the dependency graph of X. And what we actually do is not just learn the dependency graph, but also estimate the precision matrix. So we learn the structure as well as the parameters of the precision matrix. And the surprising thing here is that once you say the precision matrix is sparse, it is actually possible to do something much better than what you would without. Right? So there's a very recent work actually which said that there is some algorithm which is highly inefficient, which needs only logarithmic in the dimension number of samples to learn the precision matrix. Right? So the precision matrix is not sparse, you need O of n samples, that is linear in the dimension, whereas if you assume it's sparse, only d log n samples are enough. Now go back to the parameters. D is a small constant, 10 or 15 or something like that, and n is in the millions. So the number of samples drops down dramatically. But this result is information theoretic. It doesn't give an efficient algorithm to solve the problem. It says, okay, there is an algorithm which takes a humongous amount of time to run. In fact, on a data set of 70 vertices, the dimension was 70. Their algorithm took 2 days to run. Which obviously is not going to scale to millions of features. But the question remains, can we match this statistical bound in a computationally efficient way? Right? And that's exactly what we'll address. And before that, as I said, this problem has a lot of history, has been studied a lot in statistics as well as vision and so on. And there are several popular packages that people use, especially there's a package called Glasso due to Friedman, Hasty, and Tibshirani, which has thousands of citations across many, many different fields. And there's also more recent packages like Climb and A-Climb. These are off-the-shelf tools that you can try and fit a Gaussian graphical model to given your data set. And the main issue with this, there are many issues with these methods as for many other methods in this context. One of them is that the theoretical guarantees for these methods are somewhat weak. They are known only to work when the models have very restrictive conditions. They have to have small variances, small entries, and so on. And these are not, as we observed in practice, these are not very true for real-world data sets. And in a recent work with John Kellner, Freddie Kohler, and Ankur Moitra, we gave a new algorithm, greedy and prune, which probably learns a much simpler, much richer class of models with only logarithmic number of samples, right? Which I said is the real goal. We want to minimize the number of samples to learn the dependency graph, right? And I didn't stress the word provable here, but thinking about trying to get rigorous guarantees is what led us to this simple algorithm, which actually also works better in practice. So let me show what the difficulty is by a very simple example. So here's a challenge. I'm telling you the dependency graph of the distribution has this very simple structure, right? So the degree, the parameter d is only 3, okay? Each vertex is only connected to 3 other vertices. There is one long path, and there are some isolated 4x4 vertices. Okay, so this is the underlying graph, and this graph seems very simple, but the existing theoretical guarantees do not apply. Existing statistical guarantees do not apply. This does not satisfy this condition number being bounded assumption. And it's not just that the theory doesn't apply. When you actually test the existing methods, they perform poorly, right? So here is a plot of what happens for the error in recovering the precision matrix on this simple toy graph for the various methods. So our method, greedy and prune, is shown in purple here. As you can see, it's really laying flat, whereas other popular packages like Glasso and Climb, their error is much, much higher. Okay, is growing with the number of nodes. And another way to think about this is that our goal, as I said, is to minimize the number of samples you need to learn the graph. So let's ask, okay, I want to learn the dependency graph maybe within 75% accuracy. I don't really care about getting 100% accuracy. How many samples do you need? And here again, greedy and prune, our method, does much better. So you can see that the number of samples required to get this prefixed accuracy for the method is kind of really flat with the dimension. It's not growing with the dimension, or almost not growing with the dimension. This ties back to the complexity only being logarithmic. Whereas in this example, Glasso, it's kind of growing, looks pretty linear. Okay? And if you change the parameters a little bit, the other method also starts growing linearly, whereas our method still stays flat, which is what we really want. Okay? And in the remaining, it'll only take a few minutes to actually describe the algorithm. Right? That's a somewhat surprising thing. The algorithm is not very complicated, and one might even say it's probably the more intuitive one. So what's our goal? We're getting samples from a Gaussian distribution X, and we'd like to learn the dependency graph. And to make it more intuitive, let me tell you how to learn which vertices the vertex 1 is connected to. I'm going to only focus on one single vertex. And what happens when you actually implement it is that you'll run this in parallel for all of the vertices. So there are 2 phases in this algorithm. In phase 1, what you do is you grow a candidate neighborhood greedily. I don't know what my final set of neighbors, final set of relations is going to be, but I'll add them one at a time, right? And in second phase, maybe I go and check my work. Maybe I added some spurious vertices. I'll check if each one of them is actually necessary, and if not, I'll drop it. So that's the outline. So how does phase 1 go? How do you grow a neighborhood? So you start with the empty set. I'm not connected to anyone else. And each time step, while I haven't added too many vertices, I add one vertex, which gives me maximum bang per buck. Okay. So you should think of there's a budget in how many vertices you can add. Which one would you add first? The one that I would add first is the one that gives me maximum decrease in conditional variance. It's a simple greedy rule. You can implement it in the 5 lines of code here. So I said find j to minimize estimate something. That itself takes maybe another 4 or 5 lines to implement. Okay, so this is the first phase of the algorithm completely. You add one vertex at a time. The vertex you pick is the one which gives you the maximum bang per buck in terms of decrease in conditional variance. All right. And how do you prune out vertices? How do you filter out the things that that you might have added wrong, you do something similar. You go back and go through your list of vertices that you added, look at each one. Does dropping this change anything? If the vertex was actually essential, it should change something. There's a threshold that we set, and if dropping the vertex does not give us any improvement, then we actually do go ahead and drop it, right? So the intuition here is that each vertex in a true neighborhood should individually be essential. And that's the whole algorithm. And what we show is that this simple algorithm actually learns Gaussian graphical models with only logarithmic number of samples under a wide class of models that were all that includes all the things that people looked at before and more things that that weren't known to be learnable efficiently. And the analysis of this algorithm actually uses ideas and tools both from probability as well as graph theory, especially on viewing graphs of resistance networks and so on, and from submodular optimization, which is another field within optimization. Okay. So what we saw just now is a simple to describe algorithm which does get the desired complexity that we want in terms of sample complexity. And the runtime is also pretty fast. Right? So that's the end of the second part. As I said, I'm only focusing in this talk on the algorithms. I'm not going to talk much about the analysis and so on. And to some extent, that's because these algorithms are simple enough. I think that I can give it a high level to you, and then you can probably go and figure out the details if you so desire. Right. So the second class of graphical models that are also extremely well studied are what are known as discrete graphical models, which I'll specialize in a little bit. So to talk about learning these models, I need to first introduce some language, which if you don't follow, don't worry too much. You can still make sense of the algorithm. The algorithm is intuitive. Even if you don't make sense of this formalization, you can still, I think, gain some intuition for why you're doing what we are doing. Right? So suppose I give you a graph and I say, okay, I have some distribution on 5 vertices, and this is what its dependency graph looks like. So 1, 2, and 5 are connected, and 3 is connected to 2, 4 is connected to 5. Right? So this means in particular, for example, that 1 would be independent of 3, conditioned on 2, and so on. Right? So there's a complex set of relations encoded just by this graph, because every non-edge gives us some information. But what would the distribution of such a what would the distribution look like to have such a graph? And this was answered back in the 60s by physicists again, in what's known as the Hammersley-Clifford theorem. And they gave an explicit formula for what such a distribution looks like. And they said it's some exponential of some potential function, which here has 3 terms. It's not important of the exact form is not important, but just keep in mind that there is some nice formula for what the distribution can look like. Right? And the more general thing that they showed had the following form, that if you have a distribution X and I tell you the dependency graph is G, the formula for the distribution is encoded by the graph structure that you see. So there are these objects which are cliques, the vertices which are all connected to each other, and these cliques determine, give us a formula for what the distribution looks like. Right? And in statisticians had this other idea, which is that if I just talk about in this generality, the problem is still not solvable efficiently. You cannot solve it. It's just not possible because the complexity is too high. So they introduce this other parameter, which is called the order of interaction. Right? So here I've written a formula for distribution which has like yes or no values, and T is the order of interactions, meaning it has the specific form. And actually, even in the first talk, there was an expression which looked really like this. When Poole talked about the potential for Boltzmann machine and so on, this has its origins in physics as well. So the exact form, as I said, is not important. But what we'll talk about today is an algorithm. This is joint work with Adam Clivans from UT Austin back in 2017, where we gave an efficient algorithm which learns the structure of this binary t-wise Markov random fields with only logarithmic number of samples. Okay, and here again I'm assuming that d, the max degree, is constant, which is what we expect in when we expect these models to be useful. And the interesting thing here is that while this problem has been studied for a long time, this was the first algorithm for t greater than 2, when the order of interactions was more than 2. And the sample complexity is actually nearly optimal. You cannot do better than logarithmic number of samples, and it's also optimal in terms of the dependence on the degree d, which I didn't talk about. And the runtime of the algorithm, you cannot improve as well, in the sense that if you improve it substantially, then it breaks the hardness of some cryptographic systems, which we don't think is possible. So in some sense, this is kind of hitting the best of both worlds in terms of sample complexity as well as runtime. And while there's been a lot of previous work, they were kind of, they require much stronger assumptions. Right? So today, again, I said I won't focus on the theory behind it or where the algorithm comes from, but I want to describe the intuition for the algorithm. And the algorithm, again, as we'll see, can be implemented in a few lines. Right? So to describe the algorithm, I'll start with a toy model. It's not exactly toy because it itself has its own history and has been independently interesting, has been studied a lot in statistical physics and machine learning, image segmentation, and also in, especially in deep learning, where they show up in the form of learning Boltzmann machines and so on. But I'll just use this as a way to illustrate the algorithm. So these are Ising models. So these are distributions which have 1, -1 values. Just think of yes or no values. So very discrete. And I give you a dependency, tell you that the dependency graph of the distribution is something G, which on n vertices. Ooh. Okay, never mind. So in Ising model, basically you have weights on the edges, right? And you're trying to learn the weights on the edges. The exact formula somehow disappeared, but it fits into the same thing. It's much simpler than this because you only have pairwise interactions. So what is our goal? Our goal is to learn the dependency graph given samples from an Ising model, right? So how do you learn this? The idea is very simple. We'll try and iteratively update the weights of the edges. So there are some edges that we don't know. What will start out with some random guess for what these weights should be, and then we'll slowly increase or decrease these weights based on the samples that we'll see. Okay? And to illustrate the algorithm, again, I'll focus on a single vertex and talk about what happens there. And when you implement it, you'll do this in parallel for all the n vertices. Okay. So here's a cartoon depiction of what the algorithm is going to do. I want to learn the neighborhood of a vertex 1. So there are n vertices in total. I'm focusing on this first vertex, and I want to figure out which vertices is this connected to, which vertices does it have meaningful statistical relations to. Right? So initially, we don't know anything, so we just don't do much. And one nice thing about Ising models, which is not in general true for graphical models, but for Ising models you can do something, is that the correlations can come in two ways. You could be positively correlated or negatively correlated, right? So sometimes these two features will always agree with each other, whereas sometimes they will always disagree with each other. But both are correlations that you want to detect. So to capture this, what I'll do is to create a dummy vertex for each one first. So I break up 2 into 2 comma plus and 2 comma minus, 3 comma plus and 3 comma minus. And the sort of the thought experiment is that 2 comma plus should capture positive correlation, 2 comma minus should capture negative correlation if there is any, and so on and so forth. All right? And we don't know anything to begin with, right? We haven't seen any sample. I don't know what the distribution looks like. So I just initialize all the weights to be same. So all the edges are present in my graph to begin with. And now I get a sample. So someone gave me a sample X. How do we update my graph? We update the graph in a fairly intuitive way, which is that if the variable xi agrees with me, then it makes sense to increase the weight of the edge to the positive variant. So we reinforce the edge whenever you agree. And when you disagree, you reinforce the edge to the negative vertex. So when you agree, that means you might be positively correlated. When you disagree, you might be negatively correlated. And you keep doing this for each example. So here, when I saw this example, maybe some of these edges became darker. I see another example, some became even darker, some will start disappearing, and so on and so forth. So as you see an example, you just update each edge weight by some rule, which I haven't talked about before. But basically, when they agree, you want to bump up the weight. When they disagree, you want to kind of adjust the weight accordingly, increase the weight of the negative vertex, and so on. Okay, so that's the blueprint of the algorithm. It's somewhat of a caricature, but it's not too far from what actually works. The one most important thing that I haven't talked about is how do you bump up or how do you increase or decrease the weights? It makes intuitive sense to say that, okay, if you're always agreeing with me, I'll increase my weight to you. If you're always disagreeing, then I increase my weight, but in the negative direction. Okay? But if you're fluctuating, then there should not be any correlation, so the weight should be small. So how do you update the weights? And for this, we use something from which was developed in learning theory back in the 80s called multiplicative weights method. So it's a very simple but subtle formula that you wouldn't probably realize to use unless you had this sort of theory behind it. Okay? So the formula is simple in the sense that it updates each weight just multiplicatively. So whenever you agree, you increase the weight by a factor of something like 1.1 weighted with something. Whenever you disagree, you increase the weight of the negative edge with a factor of 1.1 or something, and so on. Okay? And the final algorithm is just, as I said, is somewhat simple. You can implement it in these 7 lines. And there's only one unknown parameter here, which I didn't even talk about. So often when you think of this algorithm, there's a lot of parameter tuning that needs to happen. But in this particular case, it's nice enough that there's only one unknown parameter that you can actually figure out pretty easily. And what we showed in our paper was that this simple algorithm actually converges to the true set of weights, true set of unknown weights of the underlying Ising model with only logarithmic number of samples. We'll recover the graph with only logarithmic number of samples. So for Ising models, people knew how to do this, but the algorithms were much more complicated and were slower, whereas our algorithm kind of matches what you can do computationally. Was the best possible computationally unless you break some other problems that we don't expect to break. And more importantly, this sort of idea of updating weights multiplicatively, that I keep reinforcing edges that are kind of having correlations, works even for higher order and much more general Markov random fields. And this was the first algorithm to do it. And the analysis, as I said, which I'm not going to talk about today at all, exploits various properties of these distributions that come from statistical physics literature. But they're not too complicated. You just have to work with these things a bit more carefully, right? So to summarize, I talked about 2 algorithms for 2 different kinds of graphical models, which are like greedy algorithm, which is somewhat simple again, and then the multiplicative weights based algorithm where you start reinforcing edges as you see new examples, right? So both of these algorithms come with some provable guarantees that we know that they will work when your model satisfies certain assumptions. And right now we are investigating how realistic these assumptions are for real world data sets. And so far our preliminary experiments say that they're actually pretty realistic. We looked at some gene regulatory networks from various databases, and they seem to satisfy or were close to satisfying one of the assumptions that we make for Gaussian graphical models. And for Ising model, we don't have that strong a restriction anyway. And as perhaps was hopefully clear, the algorithms seem practically viable. There are just a few lines of code. Their runtime is, for the most part, not improvable unless you break some cryptographic things. So how about the future? So the one thing, as I said, we are currently exploring is that these algorithms so far have been in the theoretical world. These are very recent, especially the Gaussian graphical model one is just like a couple of months old now. And we're investigating what happens when you actually try and use them instead of these packages like Lasso and Climb for real world data sets. Now that we know that they have better statistical properties as well as seem to work for some of the examples seem to work better on some of the examples that we looked at, can you actually use them for applications? So I don't think that they'll work as these, much better for the applications, but now this gives you a new wheel to crank, right? So they probably has a combination of these things which will do much better than just using the existing tools. And in terms of computational challenges, there are two very important ones which seem very challenging. For repeating the same word, but these are hidden variables. So far, when I talked about graphical models and so on, I only consider cases where you see all the variables, right? But maybe the degree of the dependency graph is small only when you have some hidden variables. So what do you do in this case? And some of the techniques that we saw here actually are known, were shown to work by other people for classes of restricted Boltzmann machines and so on, where you do have hidden variables, but it's not clear what we can do there. I think we need fundamentally new algorithmic insights to tackle these challenges. And another question is whether or not we can learn all Gaussian graphical models efficiently. So Gaussian graphical models are extremely versatile, as I said. So if you can actually learn all of them efficiently with logarithmic number of samples, that would be very useful in practice. So right now we do this for a wide class of distributions, but it's still not as general as we'd like. That's it. Thank you.
When you talk about distributions, right? Say I have a particular use case. It's a graph database, and I have some historical data where I have the relations between the nodes. All right. I want to predict what would be the future. Like say I have a data of 6 months of this graph database, and I would like to predict say what's the next 1 month dependency relation. Can I use this graphical model for that?
That's a very good question. There is actually some work on this, trying to predict on graphs, but trying to tie these two would be could be useful. I haven't thought of that before. If not directly, at least some of these algorithmic insights could be useful, especially if you're trying to do, let's say, greedy or this voting-based methods. Maybe you can use the history to do some better initialization and things like that. So probably the best way to test it is to actually see if it works in practice and go from there. So far as I know, there is some work on doing graph learning directly, but not trying to use techniques from graphical models and things like that. Especially if you have the history, then it could be useful.
In the greedy and the prune algorithm,
yeah.
So I understand you select the parameter which gives you the maximum correlation between the output and the input. And then you say you will prune it afterwards, depending on some other factor that you would have realized. Shouldn't the greedy and prune method in the greedy phase itself just identify the correct parameter? And therefore, what's the need of the pruning of the parameters?
Right. So that's actually a very good question as well. And the reason we have to do this is somewhat subtle. So basically what happens is that we're not looking at direct correlations. We are looking at conditional correlation. Right? Like, so we look at how much improvement does vertex 2 give, let's say, given all the things that I've added so far. Right, so in this formulation, the greedy method is sensitive to the order in which you will process the things. So for instance, maybe adding the 10th vertex actually decreases the bang per bug that you added first. So that's why you have to go back and revisit the work that you did.
So greedy and prune works at the same time, or is it?
At the very end, You could do it at the same time, but you don't need to really. You just do it at the very end. You could potentially do it at the same time. It should only improve. It won't hurt the performance, the theoretical performance, but you don't need to.
In the beginning, you mentioned that it took a lot of time for a data set of around 70 points to build up to a final graph, right?
Right.
So what was the most time-taking part in that? Were you trying to correlate the conditioning between the vertices that took time, or that the relative ordering of the vertices, the other vertices which are an independent set, took a lot of time to give the relation between these two vertices?
Right. So this was an experiment from another paper. The one that did this proved that it is information theoretically possible did. And there, what they do essentially is to go over all possible vertices that could be connected to. Right, so you have 70 vertices. Okay, I say the degree is 3. They essentially look at all possible 70, choose 3 options. Okay, and choose the best one, right? And 70 choose 3 is already pretty big, and you slightly increase it to 10, then it's like 70 choose 10 is just humongous.
So we have to take all the P and C's. So
Right,
is there a
exactly.
way to reduce that also so that we...
That's exactly what the greedy algorithm does.
Okay.
Instead of looking at all the subsets, it's trying to do one at a time, right? That's what you should do. And when it works, it's obviously going to be much faster.
Yeah, so in your talk you were mentioning how the gradient Proom is going to reduce out the PNCs, right? So in real world, can this be translated to reducing out very complex relations into much simpler ones?
It could. I mean, so greedy and prune, as I said, is somewhat versatile, but it's also a little sensitive. Right? If you change the order, for instance, it could actually make you pick completely different sets of vertices. So you might have to do some cross-validation or have some other intuition for why it might be a good method to try. Right? So for Gaussian graphical models, it definitely makes sense under these conditions because it's not sensitive to order in this case.
I think we'll sort of draw a line there and move on to the next speaker. Thank you, Raghu.
Sure.
Raghu actually has to run away to catch a flight in about 3 hours and change. So thank you very much. I think today is Saturday, so you'll actually